Okay, students. So in this section, section 1, we are to discuss about the moment of inertia and product of inertia, and then various properties. All of you know that what is a rigid body? A body is a system of particles, and it is termed as rigid if the distance between 2 points of the body is unchanged, or we can say is invariable. Okay. After that, the concept of moment of inertia of a particle about a line. First thing, whenever we will discuss about the moment of inertia, it will be about some line. A line will be given to we people, and we were to find the moment of inertia. Like here, a particle is given of mass m, and there is a straight line. Then the moment of inertia of this particle of mass m about this line will be mass into the square of the perpendicular distance of the particle from the line.
Arena.
Okay. So the moment of inertia will be mass into the perpendicular distance between the particle and the straight line. Its square will be multiplied. mr square, where m is the mass and r is the perpendicular distance of the particle from the straight line. This is for one particle. If we are to deal with many particles, then it will be summation mr square. Summation runs over all the particles available in the system. Then product of inertia. Product of inertia is always about two lines. Something x-axis, y-axis, or y-axis, z-axis. So if we are with a system of particles and the positions are x1, y1, x2, y2, xm, ym, and masses are m1, m2, mn, then the product of inertia of these particles about the lines ox and oy will be mass into the coefficients of the coordinates. The product of the coordinates means m1 x1 y1 plus m2 x2 y2 plus mn xn yn. So the product of inertia about ox oy will be summation I from 1 to n mi xi yi. This is for the finite case. If we are having a body, then this summation will be replaced with integration over the given interval, like from a to b. Next, it's too light. If we are to work in the three-dimensional space, so if x1, y1, z1, x2, y2, z2, xn, yn, zn be the positions of the particles, then in this time we can find out the moment of product of inertia about ox oy, about oy oz, and about oz ox. So the moment of inertia about ox oy, it will be summation I from 1 to n mi, and then when we are talking about ox oy, then the x and y coefficients will be multiplied. So mi xi yi. When we are to find out the moment of inertia about oy oz, then it will be the y coordinate and z coordinate will be multiplied. So it will be summation I from 1 to n mi yi zi, and similarly for zx it will be summation I from 1 to n mi zi xi. Now these are the notations for the moment of inertia and product of inertia. Like in three-dimensional space, when we are to deal with we are to find out the moment of inertia about ox. This time I need your imagination. Just consider a three-dimensional space. Any position like x, y, z. then the distance of this point from x-axis and the perpendicular distance, we have to find out the perpendicular distance of the point xyz from x-axis. Now to find out the perpendicular distance, what we will do? On x-axis there is a point x00 on x-axis, and now meet x00 and xyz with a straight line. Now this is a straight line perpendicular to x-axis. Try to imagine we are in three-dimensional space. There is some point xyz. On x-axis there is a point x00. We draw a line from x00 to xyz. On x-axis this line is a straight perpendicular line. So the distance of this point from x-axis will be under root of x minus x square plus y minus 0 square plus z minus 0 square. So it is under root of y square plus z square. And so the moment of inertia of some particle of mass m placed at this point from x-axis will be m into r square, means it will be y square plus z square. If we are to deal with a system of particles, then the moment of inertia will be summation m y square plus z square, and we represented it with a. If it is clear to you people, then just tell me. Anyone having any problem that how we are taking a is equal to summation m y square plus z square, the moment of inertia about x-axis? Okay, no problem. Then about y-axis, again the point is xyz. On y-axis there is a point 0 y0, and the perpendicular distance, means the distance between these two particles, will be under root of x minus 0 square plus y minus y square plus z minus x 0 square. So it will be under root z square plus x square, and now the moment of inertia is m into perpendicular distance square. So it is m z square plus x square. Summation is taken to cover all the particles. This is denoted by B. And similarly, the moment of inertia about z axis is C, which is summation m x square plus y square. Similarly, it is obtained. Keep it in mind when we are talking about the moment of inertia about x-axis. What we are to notice here, only the x variable is not present. It is the sum of the remaining variables. When we are to find out the moment of inertia about y-axis, square of other variables is taken. And similarly, when moment of inertia is about z-axis, square of remaining two is taken. After that, we are having D, the product of inertia about OY, OZ. E, the product of inertia about OZ, OX. And F, the product of inertia about x-axis and y-axis. So throughout this discussion or throughout this section, we will consider A, B, C, D, E, F in this way. Okay. Now there are some examples to have a complete idea of moment of inertia and product of inertia. Let's discuss those. The first example is, yes. In the first example, we have to find out the moment of inertia of a rod of length 2a. The rod is denoted by AB, about a line that passes through one of its ends and perpendicular to its plane. So AB is the line, the rod of length 2a. We have to find out its moment of inertia about the line AN, a line passing through one of its ends. Okay, so will be the procedure? We will consider an arbitrary element of this rod. So we have just taken an element Rs of breadth delta x. Okay. Now assume m is the total mass of this rod. Then the mass per unit will be m by 2a, because 2a is the length. M is the total mass, 2a is the length of the rod. So mass per unit length will be m by 2a. Then mass of the portion Rs will be the mass per unit into breadth of the particle Rs. So it will be m by 2a delta x. Is it okay? And now assume x is the distance between An and Rs. So the moment of inertia of the element Rs about An will be m by 2a delta x into x square. I am repeating it again. M is the total mass of the rod and the length of the rod is 2a. So the mass per unit length will be m by 2a, mass divided by the length. Now if the breadth of the portion Rs is delta x, then mass of the portion Rs will be m by 2a into breadth of Rs. It is delta x. So m by 2a delta x. This is the mass of Rs. If x is the distance between An and Rs, then moment of inertia of Rs about An will be mass into distance square, perpendicular distance square. So it will be m by 2a delta x into x square. And now to find out the total mass of the rod AB, what we will do? The x will range from 0 to 2a. At 0 it will be at A, and at 2a it will be at B. So moment of inertia of the rod about An will be integration 0 to 2a m by 2a x square dx. M by 2a is the constant term, x square, it will be x cube by 3. And now replacing the limits, we will have 4m a square by 3. Is it okay? Is there any next class? Students, is there at 3
No,
there
sir.
is? Okay. Then we are continuing it for 15 minutes again. Okay. The next example. In the previous example, we obtained the moment of inertia of the rod about the line AN that passes through one of its point, one of its end. This time, in the next example, we are going to find out the moment of inertia of the rod AB about a line that passes through its center. So we are having the rod AB, its length is 2a, and the line NC passes through its center, perpendicular to its plane. Okay, the whole process is similar. Again, we are taking a portion Rs of breadth delta x at a distance x from Cn. Then, since the m is the mass of the rod, mass per unit will be m by 2a. Mass of the portion Rs will be m by 2a into delta x. Moment of inertia of this portion about Cn will be m by 2a delta x into x square. And now, to find out the moment of inertia of the whole rod, this time the limits will be minus a to a. Why? Because Cn is in the center. So when x is 0, we are at C. When x is at A, we are at B. So to cover CA, we need the limit from 0 to minus A. And therefore, moment of inertia of the whole rod about NC will be integration minus a to a m by 2a x square dx, and it is m square by 2. Oh, sorry, m square by 3. Is it okay? It will be obtained. Next, yes. Okay. Next one, students, what we will do now, in the next example, we will use the previous articles. Means we find out the moment of inertia of the rod when a straight line passes through its center. Okay, this article will be used, and what we observed that the moment of inertia will be ma square by 3, mass into half of the length square by 3, because the length is 2a and we are saying ma square by 3. So the total mass of the rod into half of the length square by 3. This will be used in the next article. How the next article is solved? Basically, we are to find out the moment of inertia of a rectangular lamina about a line through its center and parallel to one of its edge. Sorry. Means ABCD, a rectangular lamina is given. We are to obtain the moment of inertia about OX. About OX. What we will do, just do one thing, that make some strips. The strips should be perpendicular to OX, like I have represented PQRS. We will cut the whole lamina in such strips. Okay, and now PQRS is a rod. Is it okay? PQRS is a rod, and OX line passes through its center. So the previous article can be applied here. Assume the breadth of PQRS is delta x. Now, if m is the total mass of the rectangular lamina, then mass per unit area will be m by 4ab, because we are assuming that the sides are 2a, 2b. So mass per unit area will be m by 4ab. Now, what is the area of PQRS? Its breadth is delta x and its length is 2b. PR is equal to AD is 2b. Okay, so mass of the strip PQRS will be 2b delta x into L. L is m by 4ab. So it is m by 4ab into 2b delta x. And now moment of inertia of strip about OX will be mass into half of the length square by 3. What is the mass? It is m by 4ab, 2b delta x. Then half of the length means b square by 3. Is it clear to you people? Okay, and then it is m by 2a into b square by 3 delta x. If you have any confusion, you can ask me right now. And now, to find out the moment of inertia of the rectangular lamina about OX, we were assuming that the strip PQRS is at a distance x. So the range of x will be minus a to a. Okay, and so the moment of inertia of the rectangular lamina about OX is minus a to a m by 2b 2a b square by 3 dx. It is mb square by 3, because mb square by 6a, it's a constant quantity, will be common. Then 1 into dx, its integration will be x, a minus minus plus a, it will be 2a, 2a is cancelled, so it is mb square by 3. When we find out the moment of inertia about OX, if we are to find out the moment of inertia about OY, it will be ma square by 3. Is it okay? Because in that case, we will cut the whole rectangular lamina in strips parallel to AB. and the limits of integration will be minus b to b, means the roles of a and b will be interchanged. So it will be ma square by 3. Clear? Written. Also, the next example, the proof is provided for the next part also. What is this? A rectangular lamina is given. We have to find out the moment of inertia about a line passing through its center and perpendicular to the lamina. In the previous example, we obtained the moment of inertia about the lines passing through its center, but in the plane of the rectangular lamina. OX, OY, these were in the same plane as that of the lamina. But in the next article, we are to find out the moment of inertia about ON. ON is perpendicular to ABCD. Means we can say that it's three-dimensional, x-axis, y-axis. XY, in XY plane, we are having the rectangular lamina, and we are to obtain the moment of inertia about OZ. And students, the proof is provided, but instead of discussing this proof, I would like to use the theorem of perpendicular axis that we will prove later on. But that theorem states that if the moment of inertia about OX is A, about OY is B, then the moment of inertia about OZ will be A plus B. Some conditions are there that we will discuss later on, but yes, it will be A plus B. So according to that, the moment of inertia will be 1 by 3 m A square plus B square, and it is obtained in this way, m by 3 A square plus B square. Okay, so the next one is rectangular parallelopipe. To obtain the moment of inertia of this, we will use the last example. Okay, tomorrow we will discuss it, but I wish that today you will read it up to now, and please try to read the rectangular parallelopipe case also, so that tomorrow when we will discuss, it will be easy for you people. Any problem, then you can ask me.